Welcome back to the podcast. Today, we're diving into the intricate world of distributed systems and examining how process pauses can impact performance and reliability. Whether you're an experienced developer or just curious about the technology that powers our world, this episode is filled with insights that will help you understand the challenges and solutions involved in managing distributed systems. Let's kick things off by talking about garbage collection, or GC, which is a critical part of many programming language runtimes, like the Java Virtual Machine. You might not realize it, but garbage collection can sometimes cause significant interruptions, known as stop-the-world pauses. These pauses can last several minutes, which is a big concern for applications that need to be up and running constantly, even with concurrent garbage collectors. Like the Hotspot JVM's concurrent mark sweep, there are moments when everything has to come to a halt. While you can tune GC settings or adjust allocation patterns to help minimize these pauses, it's essential to prepare for the worst-case scenario to ensure your application performs reliably. Now let's switch gears and look at virtualized environments. In these settings, a virtual machine can be suspended at any moment, pausing all processes and saving memory contents to disk. This feature is incredibly useful for live migration, which allows VMs to move between hosts without needing a reboot. However, the length of these pauses can be unpredictable depending on how much data is being written to memory at that moment. On end-user devices like laptops, execution can also be interrupted unexpectedly. For example, when you close the lid of your laptop, it suspends all processes, which can lead to delays when you open it back up and resume your work. Another aspect to consider is context switching during multitasking. When the operating system switches from one thread to another, the currently running thread can be paused at any random point in its execution. This can create what's known as steal time, especially in virtual machines under heavy load. If many threads are waiting to run, a paused thread might have to wait longer before it gets the CPU time it needs. Disk access adds yet another layer of complexity. If an application performs synchronous disk operations, it can lead to pauses while waiting for slow I/O operations to complete. Interestingly, disk access can occur without explicit calls in your code. For instance, Java's class loader lazily loads class files, which can happen unexpectedly during execution. If the disk in question is a network file system like Amazon's EBS, the latency can become even more unpredictable due to network delays. Paging can also cause process pauses. If the operating system allows swapping to disk, a simple memory access might trigger a page fault, requiring a page to be loaded from disk. When memory pressure is high, this can lead to thrashing, where the OS spends more time swapping pages in and out of memory than executing processes. To avoid this, many server machines disable paging altogether, opting to terminate processes rather than risk thrashing. In Unix systems, processes can be paused using the SIG-stop signal. This can happen either intentionally or accidentally, leading to unexpected pauses in execution. When a process is stopped, it won't receive any CPU cycles until it's resumed, which can create confusion, particularly in environments that don't typically use SIG-stop. Now, let's explore the implications of these pauses in distributed systems. Unlike applications running on a single machine, distributed systems don't share memory. They rely entirely on message passing over an unreliable network. This means that a node in a distributed system can be paused for an indefinite amount of time, while the rest of the system continues to operate. If one node doesn't respond in a timely manner, other nodes might mistakenly declare it dead, leading to a cascade of issues. The concept of time in distributed systems is particularly tricky. How can we be certain of a node's state if it has been paused? The node might not even realize it has been inactive for a while. This uncertainty can have serious consequences, especially in critical systems like those controlling aircraft or cars, where timely responses are crucial. In these scenarios, we refer to hard, real-time systems, which are designed to meet strict timing guarantees. Developing real-time systems is no easy task. It requires a real-time operating system, RTOS, that can guarantee CPU time allocations, careful documentation of worst-case execution times for library functions, and often the restriction or complete avoidance of dynamic memory allocation. While there are real-time garbage collectors, they still require careful management to avoid overwhelming the system. You might be wondering about the relationship between real-time systems and high-performance systems. Interestingly, they aren't the same. Real-time systems prioritize timely responses, which can sometimes lead to lower throughput compared to high-performance systems that focus on maximizing efficiency. For many applications, especially those that aren't safety critical, the expensive guarantees of real-time systems may not be necessary or practical. Instead, developers can implement strategies to mitigate the impact of process pauses. For instance, language runtimes can monitor object allocation rates and free memory over time, allowing them to schedule garbage collections during low traffic periods. Another effective strategy involves temporarily redirecting client requests to other nodes while one node performs garbage collection. This way, the application can continue to function smoothly without noticeable interruptions. Some latency-sensitive financial trading systems use this approach to maintain high availability. In summary, while distributed systems present unique challenges like unreliable clocks, message passing delays, and the potential for process pauses, there are ways to design and manage these systems effectively. Understanding the nature of these pauses and their implications is crucial for developers and engineers working in this space. As we wrap up today's episode, it's clear that the world of distributed systems is intricate and full of challenges. The pauses we've discussed can significantly impact performance and reliability, but with careful planning and design, we can mitigate these issues. Whether you're developing applications or managing systems, being aware of these factors will help you create more resilient and responsive technology. Thanks for tuning in, and we hope you join us next time as we explore more exciting topics in the realm of technology.